Good afternoon, everyone, and welcome to Sigmoid Tech Talk. My name is Sudeep, and I'm the Senior Manager of Marketing and Pre-Sales at Sigmoid. I would like to thank each of you for joining us today in this session. As you're aware, the topic of discussion today is optimizing nested queries using Apache Spark. We have with us Pravin, who's a Senior Data Engineer at Sigmoid. Pravin is very passionate about solving data problems using Apache Spark and big data technologies. He has been working with some large global businesses in solving their challenges in handling huge volumes of data to derive actionable insights. He will be running the session today. A couple of small details before we get started. At any point in the session, you can click on the Q&A button that you see on the webinar platform and post your questions. We will address as many as we can towards the end of the session. Before we begin, I will give you a quick introduction to Sigmoid. We are a large data and analytics company that enables business transformation by building modern data architectures. So we specialize in open source and cloud. Some of the world's largest data producers across industries like CPG, retail, pharma, manufacturing, and AdTech work with Sigmoid to solve their complex use cases. We bring in deep expertise in primarily three areas, which is data engineering, artificial intelligence, and data ops. So without further ado, I will throw the stage open to Pravin. Pravin, please take over.
Hi, everyone. So today we'll be discussing about how to optimize nested queries using Apache Spark. I'm Pravin Mehta, and I'm Senior Data Engineer at Sigmoid. So as Sudeep said, we deal about all the big data technologies around here. So let's start. So agenda for today would be like, we will discuss what are nested queries, how to create them, and then we will go on the optimization of those nested queries. So we'll see the effects on execution time when we have like multiple nested filters with multiple operators like and or. Then we'll talk about filter optimization using joins. So when we have large filter values that need to be filtered out. So we'll talk about how can we optimize filter using joins. Then we will talk about the query optimization using some common algorithms out there. So talking about what are nested queries. So if you have, if you're familiar with SQL, right? So you know that there are some subqueries that we can write inside a query. So a query containing multiple subqueries can be called as a nested queries. So suppose we have some IDs that we want to fetch from another table, and we want to filter out those IDs and filter out some values of those IDs in some another table. So we can write some subqueries where two queries are nested together. So that type of queries are called as nested queries. So nested queries can have like multiple nested filters inside them, and each subquery inside that nested query can have like multiple internal joins, unions, intersections, and the query can span multiple table or data sets. So let's see an example. Suppose we have some employees table, and we want to find out all the employees ID, name, and the duration of them in that company. So suppose we have two tables, the previous employees and the current employees. So by doing the union between them, as we do here, we could get all the employees information. And then if we'll do inner join with the employees directory, so employee directory is some table which will have the employee ID, right, and their start date and end date. So if we do inner join with employee directory, we can find the start date and end date. Then we write another query to find out the ID name, and then we have a function which will take the ended and started and give you the duration. So nested query is something similar to this. Okay. we can have like multiple filters inside them to filter out, right? So in our case, what type of nested queries that we deal with? So let's discuss about that. So nested queries, in our case, we have nested queries which can support two filter operations and an OR. And each filter column can have more than 1,000,000 values to be filtered. So there are like multiple dimensional metrics to apply filter, right? And for each dimensional metric, there can be like million of values that need to be filtered out from the base database. And the base data set, the size of the database data set can span up to more than TVs. So this implementation that we are going to discuss was implemented in our product called Sigview. Talking about Sigview, so Sigview is a real-time dashboard where you can visualize your data, download reports, get some pivot out there. Okay. So let's see what are the effects of optimization in our case. So why should I care about that optimization? So after this optimization in our case, we could see there that there is reduction. So there is reduction in total time and resources. So now the user can download the reports or visualize the data in the list time, and the resources that were used to uh, create that data was reduced, right? And we had saved a lot of cost on our infra side. So it was like more than $100 per day that we saved on our infra side, and the users had less wait time out there. So let's see how could we filter out if we have like million of values for one column, right? So generally we apply filter in the conventional way where you use where or filter operations in Spark, right? And for that, so whenever the number increases more than 10 or more than 100, then there may be a lot of degradation. So we saw that there is a lot of degradation out there in the processing time, and the query is taking a lot of time to filter out those data. And we have like million of values for one column. So how could we do that? So we thought of applying the joins out there. So joins really helped us in that case. So while applying the join, we could have one or two operations that we could support, the include and exclude. Right? So for include, we can have inner join that can be applied out there, and for exclude, we can have anti join that the Spark has. Right? So we can apply inner join for getting all the values that we want, and anti join for all the values that we don't want. So let's see some example of the nested queries that were used in our case. So if you'll see in a real-time basis, so suppose we have a data frame for cars called car df, and we want to apply some filters. So we define some filters like A, B, C, and D, right? And A is a filter where we filter the car of colors like green, blue, white, gray. Then B is a filter of type where the car is like type of electric or diesel or petrol or hybrid. Then C, car of brands, right? D on the filter on the region. So if we have these four filters and we can nest it together to form a query. So let's see if we nest it together. So we have nested query, and where we have nested all those filters like D, which is the brand, region one, C is the brand one, A is color, and B is the type. So we want all the data of car, which is of region, which is defined in D, or the color of A, or type of B, and the brand of C. So Navneet has raised a hand. So do you have a question? Is there still the echo? Let me know in the chat.
Guys, are you able to see the screen properly? Okay, perfect. Pravin, can you speak a little bit louder? I feel. I think that would be really great.
Yeah.
Okay, cool, guys. So if there is any, if you are not able to hear anything or you're not able to see the screen, please let us know in the chat so we can fix it immediately. Say yes, if that's correct.
Couldn't see the last
Cool.
echo.
Thank you, guys. Thank you so much. Yeah, Pravin, please go ahead.
Yeah. So as I define out here, I describe out here. So we have like 4 filters for that we can apply in our card here. So suppose we want to filter out all this, and we create a pass tree for that filter. So on the root operator, we can have OR, and then D is there, and on the right side we can have all the filters which is nested together with AND. So let's see what we can do with this. So if we apply a filter in base DF, car DF, right, without predicate push down, the car DF will be passed as input DF to all the leaf nodes. So if you want to apply all those filters and we pass the base DF, the car DF to all those filters, right? So the query could be seen something like this, where the car DF and the D filter is applied on the car DF. So here this denotes filter. Similar to that, C is applied in the car DF. So if you see this structure, we could see that whenever the operator is AND, we can apply some optimization out there. And if we filter out the C, we can pass the output of this as an input to the next filter expression, right? We can pass it to this A and B filter, and then that can be used as an input for both A and B. Similar to that, now if A is filtered out from the output of the C, that can be passed to the B as the operator is AND. So this optimization, we see this pattern, and this was used in our optimization technique. So let's see how we have done that optimization. So this is the JSON object that is in our case. So suppose if we have B or C and A and E or F or D, so each alphabet out here like B, C, E, F, and D, so they are filters for some DF. So let's denote them as that. So in the root we have and then we have instances. So we have operator which will be and or, and then we have instances. So instances can be a single filter, right, like A, or can be a nested filter like B or C, or E or F, or this E or F or D. So this was our offset that we have created. So each filter expression is a tree which is composed of nodes. So node will denote the filter expression, and the filter expression can be of 2 types. They can have like dimension and values, which is like a single filter, like A or B or C, right? So they can be called as filter nodes, or the combination of filter nodes when multiple filters are grouped together with an operator, right? So they can be called as nested node. So let's call this filter node as a projection filter class, and nested node as bulk filter. So talking about the rules that we applied for this optimization. So whenever we have some query, right? So each subquery is out there, like each node, if we say each subquery out there is a node, so each node need to be processed, right? And whenever there is like lesser nodes, it will take less time, less resources. If the nodes are large, then it will take a lot of time, a lot of resources. And each node will be passed a data frame as an input for processing, right? If that data frame that is sent as an input, the size is very large, it will slow the execution. So what we thought, so what if we apply a filter on that DF before sending it as an input to another node or another filter expression? So it's similar to something like predicate pushdown, where we pre-process the data frame and pass and filter and apply some filters, and we decrease the size and send it as an input to the next node. So by doing this, we could see that every node will have lesser inputs to read, thus decreasing the total processing time, right, and the execution time of each node. So in our case, where we have a nested query, where each node is nested with an operator, like and or. So the nodes can be distributed on basis of some cost, or we can define the cost, and uh, that cost can be used to apply the filter beforehand, like the predicate push down. So how to calculate the cost for each node and how to rearrange them in some order, right? So if we have calculated the cost for each node, and then we rearrange it in an increasing order of cost, like in ascending order. So we'll have all the lesser costly on the left side and the higher cost on the right side. And if we process on the same order, so we will have optimized query where for each node a process DF is sent out there. Right? So this is the technique that we have used, like calculating the cost for each of the node, and then rearranging all the nodes on basis of that cost. So by doing this, we are reducing load on the each node. So how we are reducing the load, as we are sending less data to read on, right? And by sending that, and we are maintaining a predicate push down, where we are pre-processing the filter. All right. So this is something on as predicate push down. So let's see what was our approach on and the implementation out there. So we have to find the cost of each node and lower the cost. It will be on the left side, and the hide the cost to be on the right side. So we'll find the cost and rearrange the bulk filter. So bulk filter is the nested filter out there. So we will rearrange them on the basis of the cost, and then we will process in the same order. So for finding the cost for each node, we have to find some base on which the cost can be defined. So we have an operator out there which with each filter expression, and on the basis of that operator, we can define some coefficient, and by calculating those coefficient and assigning them to each filter expression, we can define the cost for that node or bulk filter or filter expression. Right? And the cost will totally depend upon the number of nodes and the operator coefficient. So let's see an example. Suppose we have a bulk filter, right? The nested filter, something similar to this, where we have A or B and C and D, C and D or F. So we have AND as a root operator. Then we have some nested filters like A or B and D or F. So as you can see here, there is one instance of projection filter, the one is C, and there are two instances of bulk filter, the nested filters, right? A or B and D or F. So if we arrange it in some order, as the operator is and in in here, right, the root operator. So we can apply the filter on C before and then pass that as an input to A or B and D or F. So something like this. So we will arrange it according to cost. As you could see, that C will be less costly when compared to A or B or D or F, because A or B has OR between them, right? And OR will make you do union between two data sets. And so only when C will be executed to filter out, then that output can be sent as an input to this, and then the output of this can be sent to this. So let's see how we can do that. So in case of OR, so we can't apply the technique that we decide. So whenever we have to decide on basis of the operator. So if it's OR, we'll send the base DF as it is to both the filters, right? To both nodes or all the nodes inside that. And if the operator is AND, so if we have a case where AND, we can apply the optimization that we discussed, like calculating it and sending the output to the as an input to the next node. If the query was something like this, where there was no AND, right, C or, so we could see only OR is there and the root is also OR. So we have to pass our base DF, say the car DF, to all the nodes where the filter will be applied, and then a union will be done. So how we define the operator coefficient, right? So we have seen that we can do some optimization, but how to find the cost for each node and how to get there. So when talking about the operator coefficient, we assume that whenever a join is applied, so our base filter, right, is a join. So we have million of values and we apply join to filter out. So our base out there is the join filter, applying the join for the filters. So if a join is applied, right, with a filter or may not be with a without a filter, so the result may have 10% of base data if there is like include these values or include or exclude these values, right? So there may be like 10% of base data size and 90% of data will be filtered out. So we'll be getting only 10% of the data on that. So this is assumption, okay? And if we do union between two data sets, we will have to do union all or union by name, right? So this is like basically combining two data frames or two data sets out there. So based on these tenants, we define some operator coefficient for our case. So whenever there is only projection filter where only join is applied, we will give it a coefficient at 0.1 as only 10% of data is filtered out. But when there are nested queries which have operators, right, like and or, so how could we give the operator give the cost out there? So whenever there is and between the nodes, we can multiply the cost of each children and assign that the product of all those product of each bulk filter child instance as a cost for this and for of that node if there's and if there is or, we can do the sum of all the children nodes and then multiply it to 10, like sum of cost of each bulk filter instances and multiply it by 10. So here on all, we are normalizing that the cost out there as we have done out here at 0.1. So we are multiplying it with a 10. Sorry. So so now we have defined that operator coefficient. We have something that we can assign the cost for each node, maybe the nested query, a nested node, or just a single node. So how to get the cost for each node, right? So we can have this strategy, the bottom up and level order. So we'll traverse through the instance of that bulk filter. If it's a projection filter, means one single filter expression, the filter node. Then we will assign it with a point like 0.1 that we have discussed before, right? So it will be like projection filter with points, and they will have point with 0.1. If it's a bulk filter, the nested filters, then we will recursively run on the BF, the bulk filter, and on basis of each projection filter inside them, and the operator we will decide the will reduce it on basis of that. So on case of the bulk filter, if it's a projection bulk filter inside that, then we return it 0.1. If it's a bulk filter, we'll return reduce bulk filter, where we will assign the points on basis of the operator. So if it's OR, we will do the sum of all cost of all the same label nodes, and then multiply it to 10. And if it's AND, we will do the product of the cost of all the nodes at the same level. Then when we have defined the cost, right, we can sort on the basis of the cost, and we can rearrange that bulk filter. So for this also, we have applied this bottom up and level order strategy. So we will assign the cost for each node, traverse to the node, and apply sort by. So in Scala, we have a sort by method where we can pass a key and apply the sort out there. So on this that cost, the sorting is done. So we already have assigned the cost for each node. Now we'll sort by on that point as a key, right? So whichever node on the same level has the lowest points will be on the left side, and the node having the highest point will be on the right side. So it will be like sorted in ascending order. Then the sort occurs for each nested instant of BF. So whenever the bottom level, like the leaf nodes are sorted, right, then the bulk filter will be sorted out there. So when all levels are sorted from bottom up, the top level is again sorted in a similar way. So suppose we have two bulk filter and one root operator. So again, these two bulk filter will be sorted on basis of their cost. So after finding the cost and arranging them, so we can process that query, and we can apply and reduce that the bulk filter. So for that also we have applied bottom up and level order strategy. So suppose we have a graph of all the nodes with all the operators between them. If the node is a projection filter, right, we can apply bulk filter for each dimension. So we can apply the method where we will apply the join. So here, if it's a projection filter, we will pass the DF that is given as an input to that, and then apply the filter as it is a join. So we'll apply the join operation out there. And if the operator for this label, so if the operator on this level node is AND, so we'll pass this process DF as an input to the next node. So if the node is bulk filter, means the nested filter, right? So we will reduce it recursively for its child nodes. We'll reduce it and we'll reach onto this first point. So if the operator is AND, we will pass the output of that node to the next node as an input data frame. If the operator is OR, so on this, when the operator is OR, we have to do union by name, and then to drop duplicates on all data frames. So we can apply the drop duplicates later on because drop duplicates will be a bit costly out there. We can just apply the union by name, and whenever we have the last result, we can apply the drop duplicates out there. So if the operator is AND, out in this bulk filter, in the bulk filter class, in the bulk filter object, right? So there also we can have some optimization out there. So we have different nodes, like 2 nodes, and we have a base operator as AND, right? The root operator as and we have A filter and B filter, suppose. So we pass the base DF to A, we apply that filter as an A. So this is a bulk filter, sorry for that. So this is a bulk filter, so we apply the filter of A. Then we pass that output to the B filter as an input, where B filter will be applied. So on basis of OR, we are doing the union by, right? And on basis of AND, no need to do intersection or something like that. We can pass the output of the last node out there. So where if suppose we have A and B and the net AND is the root operator, so we can pass the output of the B filter as the output of the whole tree. So that also we can apply out there. So let's see an example. So I have created one of the query out there. So these were all the points that we discussed. But let's see how could we confirm that there's been an optimization out there. So let's have some query like D or C and A and B. So based on the card data frame. So if we apply given algorithm and cost optimization, right? So if you'll see here, the D will have 0.1, C will have 0.1, A and B will also have 0.1. Then A and B, the cost out here will be the multiplication of the cost of A and B. So 0.1 into 0.1, the 0.01, right? And then we have C, so multiplication of all this, right? So if we assign the cost for each out here, and we rearrange it, right? So the query will be something similar to this. So it will be this. So A and B and C. So this will be like the front side or D. And between C, A and B, right? A and B has the less cost as its multiplication of this cost, and C has only 0.1. So it will be on the left side and C will be there. Now we have rearranged our query on the basis of the cost, and we can do processing on this order. So first of all, the base TF will be passed to the A, and as the operator is OR, right? So we can pass that base TF to D also. So A and B, A filter will be applied first, and then that output will be sent to B as the operator between them is AND. So B filter will be applied, right? And then again, as you can see here, the A filter is applied, then B filter will be applied, which will have the output of A as an input. Then the C filter will be applied, right? So which will have the output of filter A, filter B as an input. The C filter will be applied. So this will be the output of A and B and C, right? And then we have OR and D. So D, for D also we can have we can pass the base TF to D as it's the operator is OR. So D filter is also applied. Then between those two, we can do a union. So as it is OR, we have to do union. So we'll have a card D of ABCD where all the filters are applied after the union. And then after this, we can apply the drop duplicates. So let's see an object that I've created and have ran in the Spark UI. Okay, so I have some figures for that, some images. So suppose we have this filter expression P or Q and W and A or B or C, right? So there are like 6 filters, and we are nesting them together with all these operators, right? And the root is and inside them they all have OR. So suppose we have some industry, some company data, and we want to filter out on basis of industry, country, type, brand, location, and company IDs, right? And we have created this nested query. So how will it look like? If we do not apply the cost and sort uh, technique that we discussed, so the DAG will look something like this. So as you can see here, there are only two broadcast exchanges. So it's the image was very large, so it may be not that readable, but you could see here there's some broadcast exchange going on. So these are joins out there. So only two is there. But when we apply the sort and we rearrange them as that technique, so you could see here, so this is the DAG of the one where we have sorted and applied the technique, right, the optimization technique. So you could see here that there are three broadcast exchanges, one out here, one out here, and one out here, right? So you could see here, this join is pre-processed before, like it is pushed down as a filter, right? And before the unions, we already have applied the join, and we have less data to apply the union. But out here, we have union. So let's see the whole figure. So we have like two broadcast sections out here, and the next are below. But if you see the optimized one, we have like three broadcast sections in front, and then the union is done. And so by this, we can say that our optimization technique can work, and it really helps when there is large data set that we want to filter out on, and all the filter values are like so. By implementing above strategies, we could see that we have optimized the logical plan of the nested query in the Spark, right? And by rearranging this, we are also rearranging the tag, right? And creating a different explain plan, which is more optimized than the previous one. And by doing this, we are pushing the filters beforehand, and that actually decreases the total execution time and cost. Right? So by using this approach, the nested queries are processed faster than before, and thus take less time for computation or for processing, and take like less resources out there. So when we have like very large data set and we have very large values that we want to filter out, so this technique can help us a lot, right? And it will save us our time as well as our infrastructure cost. Right? So optimization is kind of a big deal, actually. So thank you for listening me. You can connect me on my email, which is pravinmehta@gmail.com. Or you can connect me in my LinkedIn. So thank you all. So do you have any questions? Yeah, you can type the question in the QA. So there was a lot of reduction in time. So previously, when this cost was not applied, there was like internal joins between unions, right? So whenever we have OR operator between them, we have union, and union actually takes a lot of time, and we have droppabilities out there also. So for that, we saw 30 to 40% decrease in time, right? By using this technique.
Guys, feel free to ask your questions to Praveen. We still have time, so we can answer your questions right away.
Uh, Hi, Pranit. So I'll be answering a question out here. So he has asked like which one is faster in terms of execution time, a query involving subqueries or the one involving joins, right? So it totally depends what your subqueries have. So if you have like very less values in filter, so you can apply the conventional filter, and conventional filter is very fast when compared to joins. But if you have large data set that you want to filter out, so that's why we have applied join. And when compared to join and the subqueries, so it will totally depend upon what subqueries have. If subqueries have internal joins, internal unions, or maybe some intersections out there, or have like multiple uh, tables that they have to search, right? That the query have to search. So subquery can be like very costly when compared to join. But if the subqueries have only small filters, then that can be fast when compared to join. It is contributed to Apache Spark. No, we haven't contributed it to Apache Spark. So this was for our own product. As I've discussed, so we have our own APIs out there. So it was for that. What's the data size we were working with? What rules on it? So we had a very large data set. So we have around 5 to 8 TBs of data that we were working on. That was the base table, and we had around 20 to 22 columns like dimensional matrices that need to filter out. And for each column, we had million of values, so the user could uh, upload some CSV or some values out there, and those need to filter out. So these were the data size that we deal with. So any more question, guys? Okay, we have here in case of and we multiply the cost, but could you again tell me about or and spark? So when we have or, we do the sum of all the cost of those child nodes, and we normalize it by multiplying with 10. So also for the optimization, we're rearranging the base and the cost, right? Yeah. Yeah. So for the optimization, after calculating all the cost, we're rearranging them on the ascending order of the cost.
Guys, I think we'll just take these many questions today. If you have more questions, you can directly email Pravin or you can reach out to him on LinkedIn. We'll be happy to revert back to you. Thank you again for joining the session and joining us in this tech talk. We really appreciate it. We'll be closing the session now, and post the session, you will find a survey form which you can fill up and give us your review. Thank you, everyone, and thank you for joining.
Thank you.